we're HABET. My name's Alex Peters. I'm the team lead. I'm a senior in the aerospace department. We're actually going to go through the line and introduce ourselves quick.
I'm Daniel Hastings, senior in aerospace engineering.
My name is Alec Walczak. I am a senior in electrical engineering.
My name is Ian Green, a senior in aerospace engineering.
My name is Kristen Munhanke. I'm a freshman in material engineering.
My name is Alexander Richardson. I'm a senior in aerospace engineering.
My name is Evan Johnston, and I am a junior in aerospace engineering.
My name is Brent Charlo, and I'm a senior in aerospace engineering.
I'm Kevin Dale, and I'm a senior in aerospace engineering.
My name is Ian McInerney. I'm a senior in electrical engineering.
I'm Chelsea Velasquez, also a senior in aerospace engineering.
Okay, so now that we've been through the circuit, I'll tell you what HABET's about. Our mission is to provide high-altitude access for experiments for both faculty and students. These experiments include atmospheric data collection, as well as drop tests, and a little bit of work with the agronomy department, allowing for crop evaluations. Our project advisor is Matthew Nelson. We have an external advisor, Ethan Harstad.
Hi, so I'm Daniel. I'm the team lead for Raccoon. This year we're part of HABET because we're working so closely with them. So what Raccoon is, we take a high power rocket up on a high altitude balloon and launch it there where the atmospheric drag is minimal. Doing that, we can achieve twice the velocity that we would have launched from the ground, and thereby that translates to about 3 or 4 times the altitude. Add that to the altitude of the balloon, and it's a very effective way of reaching extreme altitudes for pretty cheaply, you know. So where we're at with the project this year, the last semester we designed and built the rocket and did a test flight. It didn't end so greatly. We had structural problems with the fins that came off at Mach 2, which I'll talk more about on the next slide. We also designed and built a launch platform for the balloon to launch from the rocket to launch from the balloon. It turned out to be kind of heavy and pretty flimsy for how heavy it was. So we're back to the drawing board this semester on that. We have a pretty nice and simple design for that. Just a aluminum extruded, it's a T-slotted rail that it's got nice rigidity and pretty light compared to the last semester. So we're pretty excited about that. And for the fins, we're designing 2 sets. And the reason for that is because at high altitude, we need a larger surface area because the air is so thin to get the right stability. Launched from the ground, however, that can lead to problems because there's overstable, you know, or the increased drag will maybe cause structural problems like last time. So we're designing 2 sets, and because of that, we designed a modular system of attaching them. So just have these aluminum tab brackets at the fin root, and we just rivet the fiberglass fins to them that way. And when we want to replace them, drill out the rivets and go from there. Currently working on analysis for stress concentrations in the fins to make sure that that's all good, but we're pretty optimistic that this is going to work. So with that, I'm going to turn it over to Alec Walczak, who's going to talk about something cool.
All right, thank you, Daniel. So another one of our projects that we are working on is the 462 Senior Design Drop Test. Now, many of you are familiar with that, but for those who are not, the seniors in aerospace work for 2 semesters to build and design a aircraft that they take it to a high altitude and then drop it. And where we come in is we take it after it's been finished and we take it to the high altitude and drop it. And right now, or I should say our previous design did not meet performance expectations, so we decided to redesign and rebuild a new structure, which you can see here. It is, what we will actually do is we attach a pin to the aircraft, and then we insert the pin into the capsule, and then we hold it together with the shear pin. and then we take it up in the air and we ignite a compressed air canister, which breaks the shear pin and then hence dropping the aircraft. We have that attached to an aluminum frame, which is much more sturdier than previous designs, and then we attach that to the bottom of the payload. Currently, we are in preliminary testing, and Ian is going to tell us more about that. Ian?
So right now we've only had one test flight, and that occurred on the 26th of September. The recovery was successful, but the actual testing of the firing mechanism failed. Mainly failed because we lost a connection of our 900 megahertz signal. And so we have a second test flight planned for this weekend. And basically, we're not going to be testing the actual firing mechanism, but we will be just testing the actual ranges of the 900 megahertz signal. And basically, we want to find out what the range is before we lose the signal. And if possible, we want to figure out if it's a problem with our system or maybe our code. And with that, I'll give it over to Kristen.
Hello. We've been asked to record the upcoming solar eclipse flight during 2017. To do this, it'll be a long duration flight. We will have an air compressor attached to the balloon and a shroud to compress the balloon. We will also have an omnidirectional antenna on the balloon and then a helical antenna on the ground for more range.
As Kristen said earlier, with the with the solar eclipse flight, it's a lot different from our regular flights. We're required to maintain an altitude for a long period of time. For this, we've developed special mechanisms that allow us to control that, such as the shroud and the compressor. This also gives us different kinds of problems in the form of the cut-down system. Normally, we just allow the balloon to go to a high enough altitude where the balloon pops and it'll come down under parachute. With the shroud and the compressor in place, this isn't as much of an option as it is otherwise, as the shroud will keep it from gaining enough altitude to pop. In order to do that, we're designing a primary gas release system, and this is what we're going to plan on using as our primary method of cut down. This will allow us to do a controlled vent of the helium and bring the balloon down under a controlled helium vent. In this way, we don't lose parts such as the shroud around the balloon or the compressor that we might lose if the balloon were to pop in a different manner. Also, due to FAA requirements, we're required to have more than one way to bring the balloon back down to the ground. Our secondary cut-down method is going to be releasing the balloon tether mechanically. Using this method, it's possible that we lose things such as the shroud and the compressor, but it's a good surefire way to make sure that we bring the balloon down under our own control when we want it to come down. For the next part, Evan will talk about Raccoon's plans for the next semester.
For this current semester, us as Raccoon, we already have ordered fins and the launch rail to start building 2 replacement fin sets from the ones we lost last semester, along with a new launch platform, which Daniel went into. And that our goal is for this semester is pretty much design or build those, since we already designed that, and test fly the launch system on a balloon at altitude to gain specifications, make sure it all works correctly and works how it's supposed to. For next semester and future semesters, we will put the fins on the rocket itself. We will do a ground launch to make sure the fins and the shear pins and the brackets hold and work correctly how they're supposed to. And then we will do a flight test with the ignition system to make sure we can actually ignite the rocket at altitude, make sure no issues with that, any sort of complications. And we will also do a full system flight in a couple semesters, make sure and test everything, the new fins, the launch system, the launch platform, and make sure it all works correctly. And now it is Brent's turn to talk.
So I'm going to discuss the semester plans for this semester for HABET. We need to train all of our new team members, because we have a bunch of them, in launch practices and procedures, so give them as many launches under their belt to make sure that they're comfortable. We've gotten one already. We've got another one this weekend coming up, so that's a good thing. More the better. We also need to test the drop system for the senior design project, which is partially this launch this weekend, and also finishing it up and making sure that it all works before they do theirs next semester. We also need to finish our design and test our prototype for the solar eclipse launch. So we need to build our compressor and assemble our radios. We also need to design a pointing algorithm to ensure that the camera points where we need it to point so that we can watch the eclipse at all times. And Kevin Dale is going to tell you more about what what we're doing in our following semesters.
All right. Our next semester, we're planning on designing and building the prototype or the actual payload for a thunderstorm flight. We will be launching multiple balloons into the air during a thunderstorm to record density, pressure, and temperature while in that cloud. This payload will include a mesh network, which will allow us to maintain communication with all of the balloons by only talking to one of the balloons. It will also include a mobile pointer, which can be mounted on a chase vehicle in order for us to keep the communication pointed at the cloud at all times. Second, we'll be finalizing our drop platform. We hope that it will be able to carry and release 3 planes by the end of its design. Lastly, we will finalize our prototype for the 2017 solar eclipse payload and ultimately launch it by the end of the semester. Here I have Alex with the budget.
As my group keeps reminding me, we are on budget. Our budget includes things that we are likely to lose throughout our flight time. While we do have a 99% recovery rate, we do have a few occasions where we have lost things. Things that we would lose would be parachutes, tracking systems. We also go through a lot of helium, so that's definitely high on our list of things we need to keep buying. Any other questions about this I can answer during the questions section. With that, we'd like to conclude our presentation and open up the floor for questions.